Good morning, everyone. And it was a pleasure for me to be sharing knowledge over this couple of days. And thank you for the invitation, especially from Dr. Pierre. Thank you for the invitation to be here. So today we'll be discussing like a feasibility study related to the application of the CO2 storage in Tunisia. So this will be our planning. We'll start with incentive and aim, the high-level screening, selected field assessment, analytical numerical modeling, risk-based operating envelopes, and we conclude with the interpretation and future work that we need to achieve. Okay? So there will be a lot of technicals. We start a little bit with incentives, then we move on to the technical sides related to numerical and simulation mainly. Okay, so the incentive and aim for the work or CO2 storage. This is the global incentives. Okay, so we need to take action to reduce climate change and global warmings, control footprint of industrial and residential activity to ensure the welfare of the humankind. Okay, so this is the global, like they are applicable worldwide. For the Tunisian context, besides those incentives, we are right now is more energy oriented because in Tunisia they rely a lot on natural gas and oil. Still there is a bottleneck in the supply, so there is an important percentage is imported recently from Algeria and Libya in terms of oil and gas. Still there is a new discoveries, okay, in this area, mainly in the Gulf of Gabes. Unfortunately, they are rich with the CO2 that can attain a level of 30%. So in order to produce, we need a viable, eventually, like a solution besides flaring. So as you can see, this is what we do typically for the CO2 and H2S, we simply burn it. So therefore, the idea of storing the CO2 like erase it as one of the solutions, and we're gonna investigate the feasibility of such solution application in Tunisia. So the aim is promote the hydrocarbon development by handling the acid and inert gas, including the CO2, and of course mitigating climate change. Especially this area is is important area in terms of industrial, and the rate of pollution is pretty high. So besides promoting the hydrocarbon development, we'll be able to improve life quality by capturing CO2 from the industrial zone and injecting underground. We started, like basically this work was conducted between the University of Tunis and Manar and other companies like Shell, the national oil company, TAPS, by screening the potential fields. Okay, so the Gulf of Gabes, as mentioned earlier, okay, this is the Gulf of Gabes, okay, contain like several depleted reservoirs, okay. So what we are aiming to do is basically combining CO2 storage with enhanced oil recovery, like to manage emission while unlocking stranded hydrocarbon resources. So we start with the screening, then ranking the different fields there, characterize the main reservoir where we're gonna store our CO2 by integrating the petrophysical property like permeability, porosity, and we do some numerical modeling, plume migration, pressure build-up, and we build the injection flow rate and time of injection operating envelopes. This is basically the whole field that we're very concerned, okay? They are located mainly, the area of study is located nearby the main production facilities and the main industrial zones. If there's field like that really small, so we do some clustering approach by combining the storage capacity of different little field to build like one clusters. Okay. So this is the data that were provided by the oil and gas company mainly. Red, it means it wasn't provided, either is not available or the company didn't want to release it. The green are basically provided, and yellow means partially provided or pendings. So the assessment methodology, okay, it was a progressive screening framework, was applied from basin scales up to the field scales. So initially we start with the phase 1, which call it country basin assessment, where we investigate tectonic, basin size, depth, maturity, accessibilities. Phase 2 is more regional assessment, distance to source, seals, capacity, injectivity, resources. And phase 3 is we investigate further the selected site from engineering and economical perspectives. Okay, so those are all the criteria. For instance, for basin suitability, we investigate geological setting, geographical setting, identification of prospective site, we investigate injectivity, storage capacity, containment. For the detailed site evaluation is basically we build our numerical models, we integrate results coming from the field and from the laboratories, and we do socio-economical characterizations. So for all the field, we investigate 2 applications, CO2 storage, mainly in terms of capacity, injectivity, and integrities. While for the EOR, we investigated the oil qualities, the miscibility, okay, and the sweep efficiencies. Okay. So those are the results of all the fields that showed a lot of potential, and they are like whatever is green is mean high favorable either for EOR or CO2 storage. If it's red, is very low or unfavorable, and of course ranging between yellow and orange from like moderate to low limited. So the screening identified 3 potential or most important field or site that we're going to investigate, which is Miskar, Ashchart, and Hazrubal. Okay, the other are marginal or they are not like relevant in terms of integrity or injectivities. Okay, so therefore we're moving forward with a more detailed investigation of Miskar, Ashchart, Hazrubal. So for Miskar is mainly is a gas field with a depleted field storage capacity of 60 million ton of CO2, and EOR 8. Ashchart is mainly is oil, with will apply only EOR there, enhanced oil recovery, while Hazrubal we have capacity storage of 16. Okay, so those are the field and the result based in the material balance investigation. This is our numerical model, and we estimate the pressure and plume propagation behaviors. So for Miskar, we find is the strongest gas storage candidates. They have a pressure maintenance and capacity of 60 million tons of CO2 storage, and enhanced recovery may exceed 90%. However, the 3 fields will have the same issue, is heterogeneity in terms of reservoir architectures and fracture system that will dominate security and behaviors. For the EOR, for Ashchart is best EOR linked storage. However, for Hazrubal will be mainly for storage applications, okay, because it's strongly depleted. They will end production there in 2030, so it will be probably the first testing site, Hazrubal. So then we move to the second phase that we achieved for our study. So is basin screening to selected field assessment. So we selected Ashchart and Hazrubal to investigate further these 2 fields, okay, in terms of capacity, depth of the reservoir or the formation that where we're gonna store, and the geological integrity and reservoir complexity. And this is the cutoff criteria. For instance, if it has more than 5 million tons CO2 storage, it will be acceptable. Otherwise, it will not be acceptable, and will not investigate further one of those 2 fields. Okay, so we'll talk a little bit about geology. So this is the formation. As you can see, is like a lot of trouble to be dealing with. Is heavily fractured with a lot of faults. This is the cap rock or the impermeable layer. This is basically where we're gonna store. This is Algeria. This is the formations where we're gonna store. Even Algeria, it's contain like variability in terms of permeability. If you know F1, F2 is different layer of Algeria formation with different permeability. Some of them are pretty low. Okay, the other is high in permeability and porosity, so potentially storage will be achieved there. Okay, so overall for Algeria formation, fractures like fracture control, as you can see here, the behavior, okay, in terms of production right now of oil and gas, and they will control the behavior during injecting CO2. So they are very variable. This is porosity distributions. This is permeability distribution. Like the value of porosity or permeability depend how close our location from the main faults. Okay, and those are the Algeria fractures family. So we conducted also some laboratories in order to refine or fine-tune the property of Algeria formations. So we conducted some lab characterization, as you can see, with thin section and scanning electron microscopy, SEM. We conducted also connected porosity, electrical conductivity, IMS, and directional P waves. Our objective, of course, is a strengthen CO2 storage screening, modeling, and risk-based design for Algeria reservoir. So we identified mainly 5 important layers that will F1 and F3 layer will be prioritized for the main injectivity. However, layer number 3, like and mainly 5, there will be a low formation factor and we'll use it to refine injectivity predictions. Some of them are tighter, or they will be representing a restriction for the CO2 or the plume propagations, layer for F4 and F7s. So those results were integrated eventually later on in our numerical model. So this study confirmed that FD1, FD2 are both like a good candidate for enhanced oil recovery and storage for the FD1 Ashtar, and for FD2 is mainly CO2 storage, but both they are concerned related to temperature, heterogeneity, and sail integrity, and of course flow segregation, with a total capacity that is theoretically will exceed 46 million tons. So those are the properties that we use it. Okay, for the FD1 Ashtar. However, like Hasrubel, like those are the property that we use it, okay, and collected from the field and laboratories. Okay, so this is the conclusion for this step. So FD1 should be moved forward through integrated EOR focused modeling and facility reviews. However, FD2 require fully coupled reservoir and hydromechanical evaluation before it considered robust field or case for CO2 storage. And that is what we're gonna do in the next step, is building our numerical models. Okay, so we are here. Okay, we are building couplet modeling. Okay, test dynamic injection behavior. So what we're gonna see, the pressure, raise, plume propagation, integrity, and demonstrate the feasibility of injection in the Hasrubel field mainly. Okay, so of course before building our numerical model we need to specify the range of petrophysics property. Porosity is ranging between 10 to 26, matrix is ranging between 40 to 100 millidarcies. We have a density of fracture of 4 per meter, but is way higher nearby the faults. In order to incorporate the fracture, we use it homogenized porosity and permeability, where the porosity that is deployed in our model will consider the porosity of the matrix plus the fractures impact, and the same for permeability, and those are the equations that we consider it in our numerical model and that were populated over our Algeria formations. So this is the model itself. Okay, so we build this as reservoir models. We calibrate our mechanical earth model initially before upscaling to the full 3D couplet simulations. We investigate injection for 30 years to see like pressure stress interactions, capability of the model. It will be captured heterogeneity critical for flow and mechanical behaviors, and predictive assessment of injectivity, plume migration, and integrity. Okay, so this is our value. It will convert in characterization into decision grade simulation tools. Okay, so this is basically the plume, propagation, and the safety factor. All of them show like the injection will be safe. This is what we are conducting right now. We are integrating the fault as well. And our objective, of course, will simulate the new well that will be injected and use it for the injection of CO2. The last part will be like this, which is called the risk-based operating envelope. In the previous phase, we used the deterministic property. However, here, we build a map where we can evaluate the probability of failure of our caprock, of our reservoir, depending on the injection rate and injection durations. So those are the whole work that has been conducted. So we developed our proper simulator using Python. We cross-matched it with commercial simulator with the CMG. We generated our risk-based envelope, and we used some machine learning model to accelerate the decision-making process. So this is the result of our Python simulators, and this is the plume after 1 year of injections. So this is the stress distribution considerates. And what you can see, this is the result of the CMG, and this colored one is the result of Python. So we see good matching between the result provided by the industrial simulators and the simulator that we built internally. And we did, of course, internal numerical credibility. We see the sensitivity of our result to the time step and the mesh size or the grid size. And we see that our simulator is robust to continue using it instead of CMGs. Those are the results in terms of pressure between the commercial and between the in-home built simulators. And those are typical results that we can get in terms of circle of Manar, pressures, stability from geomechanical perspectives. Okay? So those, in terms of how we built our envelope, basically we start with several scenarios while varying the different property from mean to max, and we determine the number of time that there was a failure either at the reservoir or caprocks, and that will representing the probability of failure, dividing by all the simulators that will present the probability of failure. So how we can use it, either we fix time of injection and we find the max rate, or we fix target mass and we choose how long we can inject before, for instance, exceeding 5% of failure probabilities. Okay, and what we found, we conduct also sensitivity analysis. We found that during injection we need to monitor and determine the exact value of in situ stress states. And this is basically the surrogate model. So we use it to make fast decisions based on machine learning. So right away, if we enter the properties and the injection rate and time of injection, it can give us what is the probability of failure. So those are the phases that we achieved so far. In terms of conclusion, of course, we come to the conclusion. So this work that we conducted so far established the complete decision-oriented CCUS workflow for the Gulf of Gabes specifically. We progressed from basin scale screenings to the field scale evaluation and coupled flow geomechanical risk-based design. The key point, potential, we see that there is a potential in Gulf of Gabes, is real, but it's concentrated of a few, field, Miskar, Ashart, and Hazrub. The fracture and the heterogeneity of Algeria will control CO2 flow, the injectivity and containment. In terms of coupled modeling, coupled simulation confirm feasibility, injectivity by highlight pressure limit and key uncertainties. In terms of contribution, like we try to build a decision-oriented workflow, link basin screening, field evaluation, and risk-based operating envelopes. And what we are aiming to achieve, like we started already, say conduct modeling with a DFN, discretized like DFN, uncertainty reduction, and integrated CCUS deployment design. So this is so far what we achieved in order to promote the CO2 storage in Tunisia. Eventually in Africa, there is a few projects. Eventually in Algeria, they tested once, like there was a failure at the Caprox. But in Tunisia, we're trying to promote the technology. There is possibilities, okay, of course, we'll see a lot of technical challenges, but still the capability and feasibility is there. So hopefully we'll, with the new developments and interest of the government, we can move forward with the application of the CO2 in the region.